Okay, so in the previous class, we have looked into hypothesis testing, and we will go into a deeper discussion on hypothesis testing and how we can, understand this with real world examples. Um, in the last class, we also went through all of them, but it is important to understand, these concepts very thoroughly. So I will just go through them once again to make sure that we understand each and every part of it. In hypothesis testing, let's start with a very basic example. And once we have done the basics, then we will talk about the types of tests to check the sum, to check the mean, the variance, and proportions. And before we go to those steps for mean, proportions, and variance, and we will understand the basic concepts related to hypothesis testing. When we understand what is a hypothesis testing, we have to make sure that we understand what is the difference between a statistical versus the practical significance. And we will be talking about the steps which we need to take in order to uh, perform any hypothesis testing. And we will also talk about type 1 and type 2 error and the p-value, which is very important. Now, what are these? These are something which we need to understand in order to perform any hypothesis on a sample and infer that for a population. Now let's start with statistical versus practical significance. Now, statistical hypothesis testing is a method of statistical inference. So what we want to do in hypothesis testing is, if we want to make some inference, how do we conclude something, right? So some of the common types of tests that we have done in hypothesis testing are comparing simple sample statistic with the population parameters. And earlier, when we talked about sampling, we said that whatever value comes out from the sample, if we take a sample and we find out the mean of those samples, that value is called the statistic, right? So statistic is something which is associated with the sample, right? And the summary of the sample is called a statistic, and the summary of the population is called the parameter. So we all understand this by now. Now, so let's say if we are making millions of perfume bottles, so you are making a lot of perfume bottles, and if the average of those millions of perfume bottles is 150 cc, this is the same example which we have seen a lot many times. So you are preparing perfumes, right? And you are claiming that the mean of the bottles, of the volume of the bottles is 150 cc. Then we say that the parameter for that particular population is 150 cc, because you are talking about the entire population. So you are saying that the mean of the population is 150 cc, right? That is for the whole population, but many times it's not possible to measure all those 1 million bottles and find out the mean volume. So obviously, if I am going for a individualization, what I can do is I can probably test 10 samples or 20 samples or 100 samples or 1,000 samples, but I cannot check 1 million samples, right? And then I can say that yes, your mean is going to be 150 cc. So finding out the population parameter most of the time is difficult, and it's impossible. What we can do is we can take out samples, as I said, like 1,000 samples or 100 bottles, and that is sample statistics. So if you take out, say for example, 100 bottles and calculate the mean, right? That is your sample. That is your sample. And based on the sample which we have drawn from this particular, say, sample statistic, we calculate the mean, and based on that we will hypothesize whether the mean is actually 150 or not, right? Whether the difference is significant enough to say that the population is actually or the mean is actually 150 cc. In addition to hypothesis testing, we will compare two sets. So we have to compare two sets, And for example, we have two machines, say, and both of these are machines are producing perfume bottles for say 150 cc volume, right? We want to check whether the volume in both these machines is similar or not. These are some of the common things which we will do in the hypothesis testing, right? So these are the type of analysis which we perform when we say statistical versus practical significance, right? Now, let's talk about one important aspect here, which is the difference between the statistical significance and the practical significance. What happens in a hypothesis testing, we will hypothesize something, right? We will assume something. Let's say in the case of perfume making company, where the volume is say 150 cc, and based on the history, we know that the standard deviation of these volumes is say 2 cc, right? This is something which is being produced. Now, if you want to check whether something has changed or not, what we want to do is we will hypothesize something, right? So how do we do that? We will assume that, so this is our statistical significance, where you say that, yes, my entire population of 1 million bottle, right? 1 million bottle has a mean of 150 cc and a standard deviation of 2 cc. Means you can assume that the result will come somewhere around 148 to, say, for example, 152, right? For one standard deviation, right? So we talked about, right? One standard deviation is 68%, two standard deviation is 95%, right? And three standard deviation is somewhere around 99.7%. So if I say it comes somewhere around 140 to 152, you can confidently say that 68% of my bottles are going to be in this range, and 95% of the bottles is going to be in 146 to 154 range, right? So this is, you are making an assumption based on the standard deviation, right? Now, assume that things have changed, right? When we are looking into, say, practical significance, we say that assume that our things have changed in the machine and the volume is not 150 cc now, and that is what we want to check by taking some examples, okay? Or we will perform some experiments, and based on these tests we can confirm whether the volume has changed or not. So the result of these tests will tell whether the mean has changed significantly, and this is statistically significant, right? Now, if we take large samples, we can find out the statistical difference for very small difference. And these small difference might not have a practical significance. Say, for example, you took out a large sample of 5,000 bottles, and you found that the mean of them are 150.1. So this is not statistically significant. You won't be tuning your machine, or you won't be servicing your machines or changing anything in the production line in order to make a small adjustment of 0.1. Okay, this is just an example. Okay, for 0.1 cc, you won't be making any adjustment. So your statistical significance does not imply that you have to perform this practically, right? So this, because if we do tuning for a small change, there might be a huge loss to the company, right? Because you will halt one machine, or the production line might get impacted. But in some cases, this might make sense to stop the production. And in some cases, if the price of the perfume is very low and the company is just making, say, 200 bottles every day, or it really might not be making any sense to stop the production and do the readjustment, right? So this is what we are trying to understand, that a practical significance will go through this course of hypothesis testing, so that we find whether the statistical difference between these, say two different items, or from one item, makes sense to perform any practical to draw any practical significance out of the data. Okay. Now we'll move into something called the hypothesis testing steps. We have talked about it in the last class. I'm just going through it. Now, hypothesis testing, when we do hypothesis testing, there are several steps which you need to take. And these steps are listed here, all the 6 steps. And the major steps which we want to understand right now is the first 2. Now, based on the comparison of the data, we interpret the result, right? When we compare between a sample and a population, right? We interpret about the data, okay? Whether uh, a change is required or whether whatever we have assumed is correct or not correct, right? So this is something which is hypothesis testing. Now, to understand hypothesis testing, let's say a person is going for a trial, okay, a court trial. This person might have or might not have committed the crime. So the basic assumption in the rule of court is that the person is innocent. The court works on this very basic assumption of innocence, right? So this is the null hypothesis for the court. So the court is saying that the person is innocent, right? So this is your null hypothesis, right? This is going to be your null hypothesis. The alternate hypothesis is something which you want to prove and want the court lawyer to prove it, right? That the person is guilty. So alternate hypothesis is the person is guilty and the person has not committed any crime. This is the alternate hypothesis. And you don't need to provide any proof for the innocence. So in court, you don't provide any, um, any justification or any, argument that the person is innocent. The court will work if the lawyer is able or the opposition lawyer is able to prove that the person is guilty, right? So you have to prove this, and the burden of providing the proof is on the person who is claiming that the person is guilty. And the court conclusion would be whether the person is guilty or the person is not guilty, right? And you would not see court saying someone as innocent, because court cannot provide or prove someone as innocent. It can pass a resolution that the person is not guilty, right? Now, if I look into the in terms of statistical terms, you can only prove whether someone has committed the crime or there are no evidence that the person has committed the crime. It applies in hypothesis testing as well. So when you perform hypothesis testing, all this applies to you, right? So if you look at this particular slide, what you can understand is the null hypothesis is the person is innocent, right? And the alternate hypothesis is the person is guilty. And to prove that person is guilty, you need to provide the proof. So when we talk of rejecting the null hypothesis, right? If you want to reject the null hypothesis and you say fail to reject the null hypothesis, that means you don't have enough proof to say that the person is guilty. So in that case, the null hypothesis will stay, right? So if you're not able to prove that the person is guilty, it's obvious that the person is innocent. So your null hypothesis, which was your original assumption, will stay true, right? So this is how you look at the scenario in terms of the court of law. And similar thing can happen for the industrial scenario for hypothesis testing, right? Now let's look into this, where with regards to an industrial scenario, you have a perfume making company, and then you are your bottle volume is 150 cc, and so every bottle will have 150 cc. And next thing which should come to your mind is that everything has variation, right? So it's not that if you pick any random sample out of the data, you will get 150 cc. You cannot have 150.000 cc. So it will have some sort of variation, right? And the variation is actually shown by the standard deviation, which we all know that standard deviation is the deviation from the mean, right? If your mean is 150, how much deviated it is from the mean. So if you have a bottle volume of 151, it is one standard deviation, or it is 1 cc deviated from the mean, right? Now, say for example, something has happened, right? And we changed the machine, or we did some adjustment, and then after you want to see the machine is still producing, the bottles with 150 cc. So to check this, what you will do is you will pick some samples from the machine and you will measure the exact volume of those samples. And based on these measurements of volume, you will make a judgment whether the machine has changed or if the machine has not changed, whether you need to stop the machine or readjust the volume and then restart the production, or there is no need at all to make any adjustment. And this is something which we want to do, if the bottle is producing 150 cc based on the sample. So in this case, what will be your null hypothesis? Your null hypothesis will be the machine is filling the bottles with 150 cc, because we will assume that the machine is innocent, right? It has not changed. The machine is innocent. It has not changed. So your null hypothesis is going to be that the bottle is getting filled with 150 cc of oil. Your alternate hypothesis is going to be the machine is not filling the bottles with 150 cc oil. So if you compare this with the court of law, this is innocent and this is not innocent. Now we have talked about normal distribution in our previous classes, and when we talk about normal distribution, we have plotted charts like this earlier, where you can see the standard deviation is going to be 2 cc, right? If it is one standard deviation, 2 standard deviation, and 3 standard deviation, and likewise if it is -1 standard deviation, right? This is your data. So based on that, if you take out sample from 1 million bottles, you'll probably have some data points which are 148, some which are 152, and some which are 154, some which are 150.01, and so on. So if you plot the data, you will get something like this. So your basic assumption in this particular industrial scenario will be that your null hypothesis is that the mean is 150 cc. Your mean is, or null hypothesis is represented by H0 or H0, okay? That your null hypothesis is that the mean is still 150 cc, and your alternate hypothesis is that the mean is not 150 cc. And then there you will see something called a lower tail test, upper tail test, and two tail test. For now, we are talking about two tail test. Why two tail test? Because if I want to check whether the machines are filling the bottles with 150 cc, it might fill with 146, it might fill with 156 or 152. So you have two tails, right? You have two tails, and your data point can be anywhere. Your data point can be anywhere. So this is why this is called a two-tail test. This is why this is called a two-tail test. If you draw a line from the mean, right, you have basically two tails. This is one tail and this is the other tail, right? So when you are saying that the volume of the machine has changed, it can either be on the left hand side or it can be on the right hand side, right? So that's why we are going to have two tails. So we have assumed that this is a two-tail test, right? But if I ask you a question that if I change the question with a small adjustment and say check whether the volume is greater than 150 now, right? So you will check whether the volume is greater than 150. In that case, you are only worried about one tail, which is this tail, right? And it is on the upper hand side of 150. So in that case, you will be using a upper tail test. You will be using a upper tail test. And if I change the question to check if the volume has reduced from 150 cc, in that case you will be looking into somewhere here, this tail, right? We will be looking into this tail, and that's why we will use a lower tail test. So for now, understand that we are checking for if the machine is still filling the bottle with 150 cc. It can either be on the upper hand side or the lower hand side. We'll go through all of them one by one. Right? Now, to understand, what would you conclude if you pick one sample and find the volume as 157 or 156 or whatever it is? So going forward, with the experiment, let's say you pick one bottle from the production line, or say 5 bottles, and take the mean of them. Right? You took 5 samples out of the data: 150, 147, 156, 152, 151, and 150. Right? And then based on that, you make a judgment whether the volume has changed or not. Just for basic understanding, we will say we pick one bottle from the production line and check the volume of that. Right? And based on that, we make a judgment whether the volume is in the machine has changed or not. Say, for example, if you go to a market, right, and there are hundreds of tomatoes, right? There are hundreds of tomatoes. There are hundreds of tomatoes, and you take out only one sample from those 100 tomatoes, right, from the vendor, and you checked it, you found it good, right? You found it good, and you made a judgment that yes, all these tomatoes are good. Please give me 1 kg of tomatoes. And you randomly checked one sample and it was not good, right? It was not good. So what you said, okay, I don't want this tomato, and you passed a judgment that the tomatoes are not good, and you went to another shop. So this is what we are trying to do here. So we took only one sample, and based on that one sample, we are passing a judgment. And it is very important to understand that, with the sample, you are judging the entire population. Okay. In all these hypothesis tests, which you will see going for, whether that's a Z test or T test or ANOVA in the subsequent slides, whatever you are doing, we are taking for the data from, say, the sample, right? And measuring the samples, and based on that, we are predicting about the whole population or passing judgment about the whole population. And that is what I'm trying to say, that under normal circumstances, the distribution of the machines will be such that you will either find 148 or 146 or 144, right? And exceptionally, you might get something beyond 156, right? You might find something which is beyond 156. You get 158 or 159, because you already know that between -3 sigma and 3 sigma is 99.7%, right? So only 0.3% chance is there that it will be greater than 156. It is greater than 156. Now we'll look into the steps of hypothesis testing. Once we have created or the alternative hypothesis and the null hypothesis, we will select the probability of error level. Right? We have to select the probability of error level. Now, for the previous example, the alternative hypothesis was that the machine is innocent. It is still, or the machine is correct. It is still producing volumes worth 150 cc, right? And the alternate hypothesis was not producing 150, and the null hypothesis was it was producing 150 cc, right? I have changed this to 1 and 2, no problem. So null hypothesis was 150 cc and alternate hypothesis was not 150 cc. So in case of a perfume bottle, we took some samples, and based on that, we estimated about the population. And when you take sample, there is always a chance of error, right? You take some samples, and based on that, you make a judgment. You can always make mistakes, and understanding that is important for us is that what level you can tolerate the mistake, right? Which is the third step here, the probability of error level. And generally we keep it 0.05. When we say 0.05 or the alpha level is 0.05, it means that we can accept mistakes up to 5% times. So say for example, if you are taking out 20 bottles, right? You can accept one mistake. So you can have a bottle which is say 153, right? Or rest 19 of them are say 150. So you can accept only one error out of 20, which is the 0.05 or 5% level. That's something which you need to establish beforehand. Most of the industrial scenario we take 5%. If things are life critical, then you go for 1%, like cancer detection, right? Or even less than that. The decision which you are taking is very important, and it might be costly, right? And at times, if it is not very important and it is not very costly, you can also go for a level of 10%, right? You can also go for a 10% level. You can go for a 10% level. For example, news classification or things which are not critical, which are not in the production supply chain, medicines, healthcare, right? So for very normal scenarios are, for example, if you have thousands of documents and you want to rearrange them into different folders, right? Or you have different tickets which are coming from Zomato, and once in a while one ticket goes to the a different claims process or goes to a different complaint process. That's okay. Okay, that's still okay. 10% is still okay, uh, because over time, when you have more and more data in the model, your machine will work pretty well, right? Okay, so once we have understood the error level, let's look into the errors. Okay, now for our scenario, let's understand the errors with the help of this table here. And we have two state of nature, which is always there, which is the reality and the conclusion, right? Say, for example, if you have a scenario where the person being convicted, so the state of nature, which is the truth in case of person being convicted, whether the person is guilty or not guilty, that is the truth. And many times you might not know the truth, with the machine volume has changed, what is the truth, right? Many times finding out the real truth is difficult, but then here we have conclusion, what you can conclude based on the test you are doing, right? So for example, in reality, so if I take example of this machine, right? I'm saying that the machine is producing with a mean of 150. This is my assumption. My initial assumption is 150. Okay. So in reality, right, the H0 is true. Means the machine is in fact producing with 150 cc volume. Right? This is true. And we concluded this based on the test that yes, this is true, and we do not reject the H0, right? We do not reject the H0. We say that, so in reality, it was 150 cc, and based on our sampling, we found it 150 cc. So both are correct. So both are a correct conclusion, right? Both are a correct conclusion. So we did not reject the H0. Okay. So this is something which we need to understand. The other scenario will be that, the machine is in reality not producing 150 cc, right? It is producing with a mean, say 157 cc. Okay. And you took some sample from those 1 million bottles, and based on that you also predicted something like yes, 150 cc, 153 cc is the mean, and this much deviation we cannot tolerate. Okay, so we will reject the H0. So we will reject the H0 and we'll say that yes, the machine is not producing with 150 cc, and we need to tune the machine, right? We need to tune the machine. So this was a correct conclusion. So these both are correct conclusions, that there might be a scenario where the mean was 150 and you also predicted this as 150, so you got a correct conclusion. And there might be other scenario where the machine was not working with 150 cc, rather it was producing much more than that or much lesser than that, and you also predicted yes, it was actually producing much less than that, so you rejected the H0. So this is not correct, right? And you accepted this, so this was a correct conclusion. But at times it might happen that the reality was that 150 cc is what the machine is producing, right? But you took out a very bad sample, right? You took out a very bad sample, and based on that bad sample, what happened is you rejected that H0, right? So a bad sampling might be you only took one sample. You only took one sample, right? And it came 159 cc. And based on that, you said that no, this is not correct, right? We have to consider this as correct, and you committed a type 1 error. Type 1 error is when the reality is true, but you concluded it as wrong, right? So this is a type 1 error. The type 2 error is something where in reality the machine was producing say 153 cc, right? The mean of the production was 153 cc, but you took a sample which was, say for example, 10 samples only, and your sample is always based on chance, right? So you took some data with say 151, 150, and 150, and so on, so 152, right? So these were your data set, and based on that you concluded yes, this is near to 150 and I think this is correct, but actually it was not correct. So you committed a type 2 error. You committed a type 2 error where the reality was that the machine was not producing with 150 cc, right? The machine was not producing with 150 cc, but you concluded that yes, it is producing with 150 cc. Okay, so you committed a type 2 error. Now we will understand this with this particular example here, right? Let's keep these two for the end. First, understand the example of fire alarm, right? In type 1 error, this type of error is called alpha error, and type 2 error is called beta error. Okay, try to understand all these scenario with example. That will be easy for you. Don't try to memorize this chart. Okay, this was just for your reference. Now, false alarm will lead to inconvenience. So what happened is you have an alarm, right? You have an alarm, and what happened is there was actually a fire. There was actually no fire. There was no fire. Okay, but your alarm was triggered. The alarm was triggered. So what happened is that you got a false alarm and you have to evacuate your building. Okay, so this is an example of type 1 error where there was no error, right? But you got a trigger. There was no error. See, type 1 error, there was no error. The H0 was true. Okay, but still you got a alarm. Okay, you have to rejected the H0. Okay, the next is the type 2 error where you missed the fire alarm. You missed the fire alarm, and based on that, this will lead to a disaster because there was a fire and your alarm was not triggered. Okay, your alarm was not triggered. So if you see this example, there the machine had a problem. See, HA is true. HA is that 150 cc, mu is not 150 cc. So the machine was actually not producing 150 cc, right? But you did not reject the H0, right? You said that no, 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 this is not 153 cc and it is 150 cc. So what you are doing, you are producing bottles with a volume of 153 cc, and in turn you are losing out 3 ml or 3 cc of perfumes for each bottle, and this will lead to a huge loss for you, right? So this is the type 1 and type 2 error. Okay, hope you understand what is the type 1 and type 2 error. Now in simple definition, what we can see is that the innocent is declared as guilty. The innocent, a person who has not committed the crime, has been declared as guilty, right? And type 2 error in the rule of court is guilty is declared as innocent. So you can always understand that this is a disaster. Type 2 error is a disaster for this situation, for a fire alarm, right? But type 1 is a disaster for a court of law, because you cannot have an innocent declared as guilty. A guilty can be declared as innocent. That is not much of a challenge for the court of law, right? But a person who is innocent cannot be declared as guilty. So that's why in a court of law, it is very important to declare, or it is the duty, right, of the opposition lawyer to make sure that he has enough evidence to prove that the innocent person is guilty, because that is the topmost priority. Okay, so what is the effect on process? Try to understand. If you have a type 1 error, right? If you have a type 1 error, and type 1 error is not a problem in case of industrial scenario, say for industrial, right? Industrial scenario, for example, if we take 150 cc, right? It is producing, say, 150 cc of volume of bottles, but each you got something as 152 cc, and you say that no, this is not correct, and your alarm got triggered, right? And after you tested it again with 2 or 3 more samples, or 2 or 3 more iterations, right, you found that no, the initial trigger of the alarm for that industrial production was wrong, right? So what it will do is it will unnecessarily increase the cost due to frequent changes. So you have to change the machine and again, and you have to halt the production. So you might lead to some revenue loss as well, right? But if, for example, your bottles are getting produced with 157 cc, right, and the alarm didn't get triggered, so it will lead to defects, right? Or you might lose out volumes of your perfume. So this is what it is, the effect on process. So when you work for a manufacturing company and you try to create a model, these are some of the things which you need to perform in order to start with the modeling process. So you have to initially start with the hypothesis, the A/B testing and everything. Now the control method. The control method usually fixed at predetermined level of 1%, 5%, and 10%. So to check this, so that we don't have this type of alpha error or type 1 error, we make sure that if we say 5%, we say 1 out of 20 error is okay, not a problem. When we say 1%, we make sure that this is much higher. Say 1 out of 100 is not a problem. When we say 10%, we say that okay, 1 out of 10 is not a problem, right? So this is how you control the method. You control the method by fixing the predetermined levels, but you cannot control type 2 error with predefined levels. You have to usually make a huge sample size. So the problem with type 2 error is that it might lead to for example, here it might lead to disaster. So you have to make sure that you have a huge sample size, and this sample size will help you to reduce the beta error. Okay, we'll go through this with examples. So if you're not able to understand, not a problem. Now, coming to the first and the second one, this is actually a producer's risk, right? The significance level. This is a producer's risk. Say, for example, if each time you have to halt your machine and retune your machine, this will increase the cost for frequent changes, and the producer who is actually producing the perfume is at risk, right? And the type 2 error is actually consumer's risk. Like if you are getting defective product from the factory, okay, the consumer might be at risk. Say, I'm not taking example of the perfume bottle, but say for example, if something is getting produced right in the manufacturing unit, and the consumer bought from that particular company, he might be at risk because he might get many defects, right? If he's not checking the huge sample size, if he is only checking say one or two, and based on that is passing a judgment that okay, the production is good, you can send this over to me, right? But if you are not taking hundreds or two hundreds of units, and performing a test on top of it and say that okay, I think this is not good because majority of your products are um, defective. So this is actually a consumer's risk. So you make sure that you are testing with a large sample in order to avoid any beta error, right? One minus error is actually the significance level. Okay, so when you say you have 5% error rate, so your confidence is that 95% are good, right? So this is called the confidence level. And the second one is power of the test, right? So you can understand that the better your beta value is, right? The better your beta value is, the less defective your product is. So this is actually the power of your test, that you are able to find out defective items from the manufacturing, right? So this is the error. Don't worry, we will go through them, all of them through examples. If you have any question, do let me know now. Okay, so we'll look into the power of test, which is actually the last point of hypothesis testing, and we'll move into more advanced stuff. So as I told you, power of test is something which is the likelihood of rejecting null hypothesis when null hypothesis is false, right? Say for example, uh, so before we start, I want to make sure that power is actually 1 minus the type 2 error. And type 2 error, if you remember, was something has gone wrong and we fail to detect that, right? Something which has gone wrong, fire alarm, right? Something which has gone wrong and we were failed to detect it. So in case of fire alarm, say the house was on fire and the fire detector or the smoke detector did not work, and we classified it as a type 2 error. So power is actually the ability to find out the change. If something has changed and you find out, this is the power of your test. So as I said, power is the likelihood of rejecting the null hypothesis when null hypothesis is false. So in case of the fire alarm, the null hypothesis is that there is no fire, right? We always assume something as innocent, right? There was no fire. An alternate hypothesis was something which was fire. So you understand now that the power is the ability of a test to correctly reject the null hypothesis. So you are rejecting the null hypothesis and correctly you are predicting that yes, there was a fire. This is the power of a test, right? The power of a test is actually detected by the type 2 error. Now coming to the hypothesis testing steps. So we all understand now that we have to first create a null hypothesis. Then we create an alternate hypothesis, and based on the probability of error, we either accept or reject the null hypothesis. So to infer whether to accept or reject the null hypothesis, we make sure that we calculate the test statistic. It can either be the t-score or the z-score, and we also understand what is a critical test statistic, and then we interpret the result. Let's understand this with an example. Now, let's pick one bottle from the production line and the volume is 153.8 cc, right? It is 153.8 cc. With 95% confidence level, we fail to reject the null hypothesis, right? So let's look into this example. Say, for example, you are producing with 150 cc as the mean, okay? And you took out one random sample and said this is 153.8 cc. Okay, so the difference which you get is 3.8 cc, and we will perform this through Python, that how this is getting rejected, or how we fail to reject the null hypothesis. Okay, let's look into this with example. Before that, I will quickly look into p-value. What is a p-value? Now p-value is the lowest value of alpha for which the null hypothesis can be rejected. Probability that the null hypothesis is correct. For example, if the p-value is 0.045, you can reject the null hypothesis at alpha is equals to 0.05. P is low and the null must go. P is high, the null will fly. So this is what we use to remember this. So let's look into this with an example. So this is your normal distribution. Okay, we all know that 95% confidence interval is for 2 sigma, right? Now, if this is 95%, so this is 95%. This is your 95%. Then this is going to be your 2.5%. And this is going to be your 2.5%. We all understand that. Now, if you say 9.05, it means that if your value comes somewhere around here, right? If your z value comes somewhere around here, you will accept the null hypothesis. So this region is for null hypothesis, and these two regions are for alternate hypothesis. Don't worry, we will understand this with an example. Okay. For now, just remember that this particular area, the 95% area, is for null hypothesis. Whatever null hypothesis you have assumed. For example, for the industrial production, you have assumed that the null hypothesis was 150 cc. And your alternate hypothesis was that it is not 150 cc. Right? So if your P is very low, right? Your P is very low. Say, for example, it is lower than 0.05. It is lower than your 0.05. Right? For example, here, your P value is lower than 0.05. In that case, you will reject the null hypothesis, because anything lower than 0.05 will be here. Right? Anything which is less than 0.05 is here, and anything greater than 0.05 is going to be here. So if your P value is very less, if your P is low, the null must go. So you will not consider the null hypothesis. You will accept the, or you will fail to reject the alternate hypothesis. And if your P value is high, say for example, instead of 0.05, it was say 0.1, right? 0.1 will obviously stay here. It will stay here. So you will accept the null hypothesis. Okay. So this was the significance of the P value. Okay. So we'll do some tests with the help of, the different types of tests. Before that, if you have any question, do let me know. We'll take a small break and we will go through the test of mean, variance, and proportion.
So that P value that we have, is it in terms of percentage? Because like you said, if it is left side or right side going to
Right.
it will not be accepted.
Right. So that's one way of looking into it, and you can ideally assume that P value is actually a percentage. Say for example, if I give you example with a percentage, we are saying that the P value is, or the alpha value is 0.05, right? So it means it is 5%. Now if you get a P value which is less than 5%, you obviously say it is either 3% or 2.2% or 4.9%, right? So if you get anything in this range, right, from 0% to 5%, you will actually reject, you will actually accept the H0, right? You will accept the H0, because if this is the region, right, P value should be less than this value, 0.05, right? 0.05 can be 3%, less than 5% will be 3% or 2%. So it will ideally lie here in the number line or in the normal distribution. It will lie somewhere around here. And this area is called the alternate hypothesis. And this entire region is called the null hypothesis. And if you get a P value which is less than 5%, say for example 8%, in that case you will say that no, the null hypothesis is correct. I'm not going to accept the alternate hypothesis.
Okay, sorry, I got confused. Before this, when you explained that 0.045 is less than alpha 0.05, so in that case, it will null must go, right?
If the P is low,
yeah,
so that is what I'm saying, right? So if the P is low, okay, if it is less than 0.05, right, the P is low, the null will go. So if null goes, what will come into picture? HA will come into picture.
okay, so we are accepting alternate hypothesis.
Yes. So if your P is low, accept alternate hypothesis. If your P is high, then you accept the null hypothesis. Got my point? So if your P is greater than 5%, if it is greater than 5%, so greater than will come obviously here. Say for example, this is your number line, right? So 0.05, anything, if this is 0.05, this line is 0.05, anything less than 0.05 will be here, and greater than 0.05 will be here. So if your P value is less than, okay, 0.05, in that case you accept your alternate hypothesis. See, P is low, null must go. So if null goes away, then alternate hypothesis is something which you accept. If P is high, right, if your P is high, if P is high, it is obviously going to be here, then the null will fly. So it means that you're going to accept your null hypothesis.
Okay.
Okay, before we go for a break, let's do a small So we'll look into 3 questions on hypothesis testing basics. Okay, just to make sure that we understand the core concept behind it. Don't worry if you haven't understood it. We will go through them with examples. Okay, this is not a confusing topic, but there are so many different topics that it might get messy at times. But when you do with Python, you will actually understand the practical significance of it. Okay, 2 more guys, please join. Okay, no problem. We'll start. One minus alpha risk is equal to, if you remember alpha risk, 1 minus alpha risk is equals to 1 minus alpha risk is going to be level of confidence, right? Level of confidence. 1 minus alpha risk. See, 1 minus error. 1 minus this alpha risk is called confidence level, and 1 minus the beta error is called the power of test, right? Okay, moving on to the next one. A false fire alarm in the building leads to an unnecessary inconvenience. Is a type of alpha risk, beta risk, consumer's risk. False alarm is not a risk. Right? So false alarm is a type of alpha risk, right? Because it will lead to a inconvenience, not a disaster. This is not a consumer's risk because consumer risk is something which is associated, production lines and all. So this is going to be a alpha risk. The last one. If the value of p is less than the alpha, we reject the null hypothesis, we accept the null hypothesis, we fail to reject the null hypothesis. P value is less than alpha. We reject the null hypothesis because if the p value is less than alpha, it will be ideally less than, say, for example, 0.05. So if it is less than 0.05, say it is 0.03. In that case, what happens is that it goes to the alternate hypothesis side and we reject the null hypothesis, right? So the answer is going to be A, we reject the null hypothesis. Good that 4 people were able to answer this correctly. Those who have not, don't worry about it. Okay, we'll look into this with more examples. Javari. Okay, so we'll start with the test for mean, variance, and proportions. So to understand that there can be different types of data set, right? You can compare only one sample at a time. You can compare two samples at a time to check, how the two different samples which we have taken out from a particular machine are behaving, right? You can take more than two samples, and based on that, you can perform analysis and kind of find inference of that data. So with that, we will first look into one sample. One sample is something which we will look into this class, at least Z test, T test, and one proportion test. We'll try to cover one variance test, but I think that would be too fast and we will not be able to understand. So we'll go through Z test, T test, and one proportion test. And then we have two sample tests for Z test, T test, pair T test, two proportion test, and two variance test. And with more than two samples, we have ANOVA. So we'll go through ANOVA. And in with this, we will also cover chi-square test and everything. So don't worry about it. So everything and anything which is being asked in a interview, or whatever concepts which needs to be crystal clear, we'll make sure that you understand each of them. So let's start with one sample test. So before I start with one sample test, we have to understand that Z test and T test are actually tests for the mean. Okay, Z test and T test are actually the test for the mean. So for example, if I look at here, these two are for mean, right? This is for proportion, this is for variance, this is again for mean, these three are again for mean, because we have Z test, T test, and pair T test. And then this is also for mean. Okay. And with each of these topics, I will go through, how, what are these called in, different, in different ways of analysis. And then we will look into areas which are very gray. Okay. For example, should we take more than 10 samples or should we take more than 5 samples? Some books have 5 definitions and some have 10 definitions. So we'll make sure that you understand each of them correctly. So if you remember the hypothesis testing steps, we covered the alternative hypothesis, the null hypothesis, the probability of error level, which was 0.05, right? And next is we calculate the test statistic. This test statistic is something which can be either, the T test or the Z score, or the T score or the Z score. And then based on that result, we will compare this with the critical test statistic, where the P value will also again come, and we will interpret the result, whether to accept or reject this. Now, conditions for a Z test. So before I start, I will try to make sure that these are, generic. These are very generic definitions. Okay, up until here. The differentiation factor here is with this. Okay, try to remember this, that what is a Z test. So before I start Z test is done on random samples. Okay, this is done on random samples. It means you will take data at random from, say, for example, if you have 100 perfume bottles or 200 perfume bottles, you take random samples out of it. Okay, and each observation should be independent of other, right? It can either be sampling with replacement. So for example, if you have a bag, right? If you have a bag and in that bag you have 4 red and 4 blue balls, right? So it can either be sampling with replacement. So if I ask you what is the probability of getting a red ball, so you'll say 4/8. And if I don't replace the red ball, the next time the probability of getting a red ball is going to be 3/7, because you are not replacing, right? But for a Z test, we will do a sampling with replacement, right? So you will replace, you take out one red ball and the probability is 4/8. You put the red ball back again and you again take it out. So your probability is 4/8 for each instance. If you are not performing the replacement, right? So this replacement size should not be more than 10% of the population. So it means that This is something which you need to understand, that whenever we do a Z test or a T test, we make sure that the sampling size should not be more than 10% of the population, right? So the sampling, say for example, if you have 1,000 perfume bottles, so the sampling which you will perform, the sampling on which you will perform the analysis should not be more than 10% of the population. So it's not be more than 100 plus. Okay, so the sampling should be ideally between 1 to 100. Okay, but this is not the differentiating factor of a Z test. The differentiating factor is that the population is normally distributed and the population standard deviation is known. So if you have your standard deviation known, if you know the standard deviation, right, either it's 2 cc or 5 cc, right, this is your standard deviation which is known, or your sample size is greater than 30. So if I give you a problem statement where you know the standard deviation, right, or you know that the sample size is greater than equals to 30, in that case you will be using a Z test. So you will use a Z test where you know the standard deviation or the size of the sample is greater than 30. Got my point? If your size of the population sample is greater than 30, means you are taking more than 30 samples or 30 sample data, right, out of the population, then in that case you'll be using a Z test. If you are less than 30 sample size, you will be using a T test. We will come back to this later again. So for now, understand that Z test has two things. One is standard deviation and one is the sample size. Okay, as simple as that. Don't need to remember all these points. You just remember that if your standard deviation is known to you, if your standard deviation is known to you, or your sample size is greater than 30, greater than equals to 30, in that case, you will be using a Z test. Because you know that Z test and T test both are for mean, right? Z test and T test both are for mean. Then what is the difference? When to use a Z test and when to use a T test? So you'll use Z test when you know the standard deviation or the sample size is greater than 30. Got my point? So what type of questions might be asked to you? Say, for example, you have a scenario that the perfume bottles producing 150 cc with standard deviation of 2 cc, 100 bottles are randomly picked, and the average volume was found out to be 150.2 cc. Has the mean changed, right? And the confidence interval which you are looking at is 95% confidence interval. Now, in this case, straight away you can say that yes, I can use a Z test. Why? Because I know the standard deviation, right? And the number of samples is greater than 30. It is 100 here. 100 bottles are randomly picked, right? So in this case, you will be using a Z test. Any question before I proceed further? Okay. Now, one thing which you need to understand is how to calculate the Z value, right? For a T test, the Z formula is this. Z is equals to X bar minus mu by sigma by root n. If you remember, sigma by root n is something which we talked earlier when we were talking about central limit theorem. Sigma by root n is the standard error. Right? So if I want to calculate the Z value, okay, if I want to calculate the Z value, I can use this, right? So if I use this formula here, so this will be X bar is actually this. X bar is this. This is going to be 150.2 minus mu. The mean is 150, right? Divided by. Then you have your standard deviation, which is 2. So you can write 2 divided by root under of n. Can someone tell me what is n here?
100.
100. Okay, good. So this is going to be 0.2 divided by 2 by 10. So this is going to be 0.2 divided by 0.2, which is 1. Hope you all understood how the Z value came to be 1 here, right? So the Z value is 1. The Z value is 1, right? Now, if you remember, there was one chart we all talked about, which was, or we have all have seen, it is the Z score chart, right? It's the Z score chart. From the Z score chart, you can basically find out the Z critical value for 95% confidence interval. And if you look at that chart, okay, I don't want to go to that chart because it is not required for our understanding. If you go to that Z score chart for 95% confidence interval, you will get a Z critical value of 1.96. Okay, you will get a value of 1.96. Now, if I plot this over a normal distribution, right, try to understand, this is your Z calculated. This is your Z calculated, right, which is 1. Z calculated is 1. This is what we have calculated. But from the Z score chart, your value comes out to be 1.96. Your value comes out to be 1.96, right? So now your Z, so if this is 1.96 and this belongs to your 5%, right? From this 5%, this is actually what you have got, right? From the 5% chart of the Z score, you have got a value of 1.96. So if you compare 1 and 1.96, you can obviously see that 1 is actually, this is what we have understood. This is alternate hypothesis, and this is your null hypothesis. So if this is 1.96 here, here it will be minus 1.96, right? So you understand that your Z calculated value lies within this range, and this range is actually your null hypothesis. This is your null hypothesis, right? 1 comes before 1.96, right? So your Z calculated value lies within this range. This lies between this range. So you will accept the null hypothesis. You actually are not able to prove that the alternate hypothesis stays true, right? So you can, from this, you can infer that, yes, my mean of this particular statistic is going to be 150 cc. So this is how we perform for a Z test. Any question, do let me know. I hope this is clear, but it might also be a little confusing. So if you have any confusion, do let me know. So if I go back to this, right, here you can see that there were different steps. The first step was to state the null hypothesis and the alternate hypothesis. So if I go back, yes, I have stated my null hypothesis, right, and alternate hypothesis. Null hypothesis is always the same, that the machine is good, the machine is innocent. It is still producing at 150 cc, right? And the alternate hypothesis is it is not producing 150 cc volume, right? So these are the two things which you have understood now. The third is select the probability of error. How to get the Z critical? Z critical is something which you get by a chart. Okay, I don't want to, okay, if I can show you the chart. You remember this chart? if you remember this chart, what you get is a Z table, right? You have different type of Z table. This is your Z table. So from this Z table, 0.05, so 95% confidence interval is what? 5% error. So from this 5%, you calculate your Z score here, right? From this Z, so if you find the Z score here, it's coming 1.96. Okay, and you put this 1.96 in this here. So this is what you are calculating, and this is what you are getting from the chart. Okay, I'm not showing you the chart because it might get little confusing, and we will calculate this using Python. So no need of looking into the chart. So this is how we used to calculate, or back in 1980s or 1970s, people used to calculate. After that, we have different statistical functions and statistical tools. Okay, any question, do let me know before I move to the second example. Okay, I would rather ask you to go to the second example, and if you still have confusion, do let me know. Okay.
Yeah, so here in this example, since Z cal is less than Z critical, so that's why we have accepted null hypothesis, right?
Right. So instead of going through the p-value scenario, right? Instead of going through the p-value scenario, I'm just showing you how to calculate this using Z-test. Okay.
Right.
So for Z-test, yeah.
So for this given Z value, Z cal, from chart we have gotten 1.96, right?
Right.
So for some, so will there be a case that Z critical is less than
Yes.
Z value?
Yes, it can happen.
So my question is, in that case, why can't we put just limit on the Z value, that if Z value is less than this, then in that case we will not accept the null hypothesis, because it seems like an extra step that that we have the Z value, we are going to chart and we are seeing again. So there will be some value, like let's say 0.5, after which the Z critical for the Z value is becoming less than the Z value.
No. So if you want to understand this in that way, your Z score table is constant. Okay.
Right.
Your Z score value is constant. Now instead of 150.2 cc, if I change this to 160.2 cc, your Z critical value will come somewhere around 2.3. And if you see this chart, 1.96 is 5%, 2.3 will come somewhere around here. In that case, you will accept the alternate hypothesis and you will reject the null hypothesis.
Sorry, can you repeat, please?
Yeah, so what I'm saying is, say for example, the question has changed. So instead of 150.2, it got changed to 160.2. Okay, the average volume is now 160.2 when you randomly picked 100 bottles. Okay, and when you calculated the Z calculated value by using this formula, okay, that is 160.2 minus 150 divided by 2 root under of 10. In that case, say suppose it came out to be 2.3. Instead of 1, it came out to be 2.3. Now you know that the Z critical value at 5% is 1.96, right? Is 1.96. And earlier Z calculated value was here because it was 1. Now since this is 2.3 in the number line, you can always understand that 2.3 is greater than 1.96, so it will come somewhere around here.
Right. Okay. So I thought that Z critical is based on Z cal, but it is, like you said, it is based on the confidence interval.
Yes, this is confidence interval. So if your confidence interval also changes, say for example, it changes to 97%, so you have to again look back into this table, and based on this table, say for example, it comes out to be somewhere around 1 point something or something like that, right? In that case, you will put or change the confidence interval value or the Z critical value to 1.96 to say, for example, 1.99. Got my point?
Right. Yes.
So Z critical is, I'll just quickly remove this, erase this. So Z critical is related to your confidence level or interval, and this is calculated using the chart. Okay, and Z calculated is something which is calculated from the data, and you compare what you get from the data or the sample data with the Z critical value of the chart. Okay, and based on that you make an assumption whether to accept the null hypothesis or reject the null hypothesis. Okay, let's move to the next one, which is the example number 2. If you remember, there is only one thing which has changed here. Okay, the one thing which is changed here is, has the mean volume changed, right? And it has now changed to increased. So if you see the previous one, we were calculating, has the mean volume changed? So the mean value can change either in the left hand side or the right hand side of the chart, right? So if you have a normal distribution, and if I say my mean value is 150, it can either be less than 150 or greater than 150. So it was a two-tailed test. It was a two-tailed test. It was a two-tailed test because you have two tails here. Now the question has changed. It is asking whether the volume has increased. So when you say your volume has increased, right, you are actually looking into this part. Your volume has increased, this part, right? You're not considering this one. Okay. Now to understand one thing, Z scores have different types of table. Okay. Z score have different types of table. This table, which I was showing earlier, is for something which is a one tail test, which is a one tail, because you can see there is only one tail into consideration. And the other table is for this type of chart, which is a two tail test, where we are considering both these areas, this area as well as this area. For now, since you are only focusing on if the mean value has increased, right? Increased. In that case, you are using this chart. This chart will be very different from if it is for a two-tailed test. So if I can show you over. No, I don't have the chart here. But now understand that we have two different types of chart, one for the one tail, and then the different types of tails we have already talked about. See, we have the lower tail test, we have the upper tail test, and the two tail test. The two tail test looks something like this. So you have your confidence interval here, right? So this is your 95% and 2.5% and 2.5%. So this is a two tail test because you have two tails here. Then you have the upper tail test, which I have shown you over the slide, which is the upper tail, because you're considering anything which is greater than 150. So if your mean is 150, upper tail test will show you anything which is greater than 150. So this is your upper tail test. Okay. And the lower tail test is something like this, where you have your lower tail less than 150. Okay. And all these three type of tests will have different type of Z score chart. Okay. You don't have to worry about the chart because we will be calculating it using Python. Okay. Now, if the question has changed, where we are saying that the volume has increased instead of changed, So obviously, when we are looking into increased, we are looking into something called the instead of two tail test, we are looking into one tail, which is the right. We are looking into the upper tail test. Okay. Okay, so from the upper tail test, you can understand the Z critical value is again going to be the same because nothing has changed with the data. Nothing has changed with the data. The mean is still 150. The standard deviation is still 2 cc. The bottles are again 100 samples, right? And the average volume is again 150. So if I calculate it again, it is not going to change. So you have 150.2 minus 150 divided by 2 root under of 100. So this is going to be 1. So your Z calculated value is 1. Now the only thing which has changed is your Z critical value. So instead of 1.96, this is 1.65. Right? 1.645. And this is your Z critical. And still now you can see that your Z calculated value is 1, which lies in this area, which is the null hypothesis. It lies in the null hypothesis. So you will actually accept the null hypothesis and you fail to accept the alternate hypothesis. So your null hypothesis was that the bottle is still producing with a volume less than or equals to 150 cc. Any question? So what you do, the first step is to find out your null hypothesis. The null hypothesis is that so if I am asking whether your volume has increased, right, whether the person is guilty, right, you will say no, the volume has not increased. Okay, so you basically say the null hypothesis either it is less than or equals to 150, right? The person is innocent. Then you create your alternate hypothesis. Obviously the alternate hypothesis is going to be what you are trying to prove, right? The lawyer wants to prove that the person is guilty, right? The volume has increased. So in that case, the second step is to get the alternate hypothesis, which is mu greater than 150 cc. The third step is to check the significance level. The significance level is 95% confidence interval. So we can say that the significance level is 0.05. Right? 1 minus confidence interval is actually the alpha value, which is 0.05 or the p value. Right? The fourth step is to calculate the Z or the T score. So for here, we are using a Z test because we know the standard deviation and the number of samples and everything, right? So the fourth step is to calculate the Z value from the formula. The fifth step is to find the critical value, the Z critical value. The Z critical value is 1.645. Okay, and the sixth step is to infer. So these are the 6 steps which you need for a hypothesis testing. Either it's a Z test or a T test or the ANOVA or whatever it is. Okay, so you infer that yes, the Z calculated value is less than the Z critical value. So that's why I will accept the null hypothesis and I reject the alternate hypothesis. Okay. We will go through this with Python example. Don't worry about it. And we will actually see what is required from our end. Okay. Now coming to the condition of t-test. So we all know that this is generic. I'm not going back to this. This is again same. This is exactly same for Z test also. The critical part is here. The population is normally distributed and the population standard deviation is unknown. We don't know the standard deviation. In the previous case, where we were looking into the Z test, we know the standard deviation. It was known, right? In a T test, the standard deviation is unknown. And the sample size is also less than 30. So your sample size is less than 30. Okay, so this is only the two cases that you have unknown standard deviation, right? And sample size is less than 30. Is less than 30. Okay, and in the Z test was that the standard deviation was known or the sample size was greater than equals to 30. Okay, let's look into one example to understand this. Perfume bottles producing 150 cc, 4 bottles are randomly picked and the average volume was found to be 151 cc, right? With the standard deviation of sample bottles, right? The standard deviation of sample bottles is known, not of the population. See here, the standard deviation of the population was known. This is the population standard deviation of 2 cc, right? For the perfume bottles producing 150 cc, the standard deviation was 2 cc. In this case, the standard deviation of only the sample is known. Obviously, if you have 4 bottles, you can easily find out the samples, right? Standard deviation. Has the mean volume changed? So you are again asked to check whether whether the mean value has changed or not. Okay. So in here, the question is, has the mean value changed, right? So obviously the null hypothesis is going to be no. The null hypothesis has not changed. Okay. So the null hypothesis is mu is equals to 150 cc. This is the first step. The second step is the alternate hypothesis is just the opposite, right? So the null hypothesis is not 150 cc. It has changed, right? The formula to calculate the T score or T calculated is again m minus mu by s root under of n. Okay, obviously this is again the same 151 minus 150, right? You have s, which is 2, which is s is actually the standard deviation of the sample, the 4 bottles which you have picked up, and then you have divided by root under of 4. So this is going to be 1 divided by 2 by 2, which is 1. So your T calculated value is 1. Right? Why we used a T test here? Because the sample size is less than 30. It is 4. Right? And we only know the standard deviation of the sample. We know the standard deviation of the sample, not the population. Okay, and we are trying to find, has the mean volume changed? It can either change in the left hand side or the right hand side. Means it can either be greater than 150 or less than 150, right? Or it can be 150. So it is actually a two-tailed test. Okay, so you calculated that the T statistic, or you can say T calculated value. So this was your third was this. So your significance level is 0.05, or the alpha value is 0.05. The fourth part is where you calculate the T calculated value, which is 1. Right? It is 1. And your fifth is to find out the critical, T critical. T critical is again, you have to find it through a chart. Right? And that chart, I have made 2 instances here. So since this is 0.05 and this is two-tailed, right? The critical value which we can have is 3.182. The critical value is 3.182. And for a T test, remember, you have degree of freedom. We call it degree of freedom. Degree of freedom is generally n minus 1. N here is 4, so n minus 1 is 4, so it is 3. Right? So obviously you can understand that there will be a chart, right, where you have degree of freedom on one hand side, so it is 1, 2, 3 up until 29, right? Because if you have greater than 30 samples, it is not going to take t-test into consideration, right? And then you have different significance level 0.01 and 0.02 and then 0.05 and so on. So from this, if you find out degree of freedom 3 and your alpha value is 0.05, the value will be 3.182. This is actually we have from the table, the T table, the T score table. And the critical value is 3.182. Okay, so this value is going to be 3.182. Right? Again, you plot a graph, normal distribution, right? Your T calculated is 1, and your T critical is 3.182. Right? Obviously, this is 1, so that's why it is on the left hand side. And based on our hypothesis testing, we know that if it is greater than 3.182, it will lie in this area, which is the alternate hypothesis. But since it lies in the H0 area, we are accepting the H0, right? And we are rejecting the alternate hypothesis. Any question? I will go through it again if you have any question. The formula and the entire background is same for Z test and T test. The only difference is that in T test, you have less than 30 samples, right? And you don't know the standard deviation of the population. Don't shy away from saying that I didn't understand a single word. I'll go through it again. Okay. So this is how it is calculated. It was calculated back in 1980s and 90s when statisticians used to do this on a paper pencil, right? Now we will move on to the next one, which is the one proportion test. But before that, I just want to show you through Python how can we perform Z test and T test, and how can we look into a basic example of a hypothesis testing. Okay, with that, please open your Python notebook. Let me know once you have opened the notebook. Okay, Bhagat is ready. Dina ready. Okay. Question ready. Okay. Great. So we'll start. Let me take one example. Check if I can take an example. Okay, let me take this example. So this is just a normal hypothesis testing. Okay, I'm not going through t-test and z-test now. This is one of my example where I say pick one bottom production line and the volume is 158 cc with mean of of 150 and standard deviation. Let's change this to 4 box. So in here we will do this step by step. Okay, say I do this by step 1. So step 1 is going to be that my null hypothesis is mean is equals to 150 cc. Right. So with that we can say that the null hypothesis is that the mean is 150 cc. Step 2 is alternate hypothesis. Right. There are 6 steps if you remember. Alternative hypothesis mean not equals to 150 cc. And the third one is going to be that 0.05. I can write alpha is 0.05. Right. So it is not given 95% interval, but I'm assuming it's a 95% confidence. So the alpha is 0.05. Right. 0.05. This is what we have as steps. Now we have to find out the Z calculated value. Z, step 4 was what? Step 4 was Z calculated. Right? I'm doing this very slow so that you also understand. Now we all know that Z calculated was something called observed mean minus population mean, right? divided by the standard error. Right? Standard error was standard deviation divided by, I will write just root of n, square root of n, so that you understand this. Okay. This step 4, observed mean minus population mean divided by standard deviation by root under of n, square root of n. Okay, so let's start with our import numpy np. So I'll be using this later, so I'm using import pandas as pd. What else? If I need to plot something, import matplotlib dot pyplot as plt, right? And import bond as essence, right? Okay, so we all know these first 3 steps are, that doesn't require any calculation. The only thing which we need to find out is z calculated. So let's find out z calculated. Z calculated is equals to 153 here, 0.8, right, minus 150, and then divided by, you can write 2 is the standard deviation divided by NP, okay, the z calculated value is coming to be 3.8, right? It's coming to be 3.8. If you want to use the math function, you can do that. Okay, I'm just using the numpy because I'm comfortable using numpy. If you wish, you can use this also. Just commenting this out. And instead of np, you can use math.sqrt. Right? You can use your math, not a problem. So the z calculated value is 3.8. Right? Now, if you remember, we have to understand that whenever we are using hypothesis testing or calculating anything for hypothesis testing, always the data should be a normal distributed value. Okay, it should always be a normal distributed value. Okay, so let's use the normal function. If you remember from the last class, we used something called from SciPy dot stats, right? Import norm, right? So I'm importing the normal distribution, and let's find out the p-value. So I told you that here with Python we'll be using the p-value, okay, not the z value or the z critical value. Rather, we will directly find the p-value from the z calculated value. So we will use 2 into norm dot sf. If you remember sf was the survival function, right? And if you pass the z underscore calculated value, so it will give me the p-value. So the p-value comes to be 0.000144, which is less than the 0.05 significance value. So we can write one statement here that compared to the alpha value of 0.05, the p value is low. So if you remember what I said, if p is low, right? If p is low, null must go. So we will reject the null hypothesis and we will accept the alternate hypothesis, right? So null will get rejected. Okay. So your alternate hypothesis means mean is not equals to 150 cc is correct. So from this example, you can say that yes, the mean is not equals to 150 cc, or the person is not innocent, he is guilty. Understood? What we did, we first calculated the z value, okay, or we calculated the z. The z value came out to be 3.8. We use this 3.8 in the normal function, okay, because if you remember, we are using a normal function everywhere. We are using a normal function everywhere. You see, we are using a normal function. This is a normal function. So we are checking this with this survival function, which is norm.sf, and passing the value 3.8 just to check what is the p value for this particular z score. And it came out to be very less than 0.05. And as I have said that if it is less than 0.05, right, the null must go. And we will reject the null hypothesis and we accept the alternative hypothesis. Any question? Do let me know. So I showed you two ways. One is the way it is calculated, right, through the z scores, and the other is the p value with Python. So here I showed you with something called the z critical score, and here we are showing it with the p value score. Any question? We'll go through a couple of more examples. Right? Any question? Okay. I'm showing you one with one sample z test. One sample z test. If you're not able to understand, don't shy away from asking questions. Okay. But let me show you one sample z test. It is actually in the similar line. Okay. So I will just copy few. Okay. Z test is actually not available in the SkyPy library. So the library we will use was stat models, I believe. You check stat models dot stats. Import.
It is from start model.
Yeah, it's from stat models dot stats.
No, it is import in the first line. So I mean the first.
Oh, okay. Sorry. From, yeah, thank you. So stats models, models. Yeah. So from stats models dot stats, import weight stats. Okay. Why I'm using this? Because Z test is not available in the usual, the SciPy stats library. So I will also use import SciPy dot stats. We can obviously use SciPy, but in another way as stats. Okay. Test. Okay, so this is your libraries which you need to import. Now let's do this with data set. So I have a data set with machines and this has a lot of random data or 100 random data for the same example where the mean was 150. Okay, so you can see data varying from more than 150 to less than 150, right? So let's use this data and we can import this in a data frame. df is equals to pd dot read underscore csv, then machines, right?
Trying.
Yeah, we'll try. Okay. Others, please also try to download the data. Open your WhatsApp web. From the next class onwards, I will share the files with you beforehand. Okay, so let's start. Those who are able to download, please download it, or else you can follow this video, probably not more than 20 minutes, right, is left. So we'll quickly go on to import the data machine1.csv, whichever I have shared. The data frame, you can see these are the 100 rows. Okay, and then if I do a df dot describe, what I can see is I can see the number of counts, which is 100. Mean is 150.2. Standard deviation is 2.01. Right? And the percentile values and the max values. Okay, if you can go back to the slides. Yes, this is the one I'm talking about, right? 150 cc is the mean, the standard deviation is 2, and the 100 bottles are randomly picked, and the average volume was found to be 150.2 cc. Okay, so let's go to the next step. So we have looked into the statistics. Now let's try to plot this. We have all seen how to plot this SNS dot this plot. We have 10 data points, and now the data is going to be df, And let's put a label saying this is machine 1, right? Okay, show. So the 100 data points are plotted here, right? You can see the maximum value is 154 somewhere, minimum value is 146 somewhere, right? And let's plot a box plot, right? I hope we all know how to plot a box plot. I will quickly copy this. Work cap to see df and y is equal to machine 1 and kind is equal to box, right? Okay, so this is your box plot. You can see that the mean is a little bit above 150, so 150.2, whatever we have seen in the descriptive statistics part, which is 150.2. Okay, you cannot see any outliers. No data point is outside this quartile range. And then let's look into the stats model package. So we will use build stats dot z test, right? You can see the different types of tests which are available. You have t-tests as well, right? I will use the z test here. Okay, so z test, and then the data is in machine space 1, right? This is my data frame, I believe, right? The mean for our population is 150. I'm passing the value as 150, and in this case we'll use alternative, which is two-sided. This two-sided because we have two tails here, right? And the question which was asked to us was, has the volume changed? Since the volume has changed, whether it is increased or decreased, that is not told to us. So it can either be on the left-hand side or right-hand side. So we will be using two-sided. Okay. Alternatives is equals to two-sided. Let's run. Okay. So what we are getting is, we are getting the Z calculated value, right? The Z calculated value as 1.00603. Okay. 1.00603. So if you come back here, we also got a Z calculated value of 1, right? And the P value, this is the P value. Okay. The P value is 0.31439, right? Which is much larger than the 0.05 threshold, right? So we can copy this from here and we can say that compared to the alpha value of 0.05, the P value is high. Null will get accepted. Okay. So now we understand. That if we have, okay, if we have a plot like this, the P value for our scenario is 0.05. Right? Ideally, if anything less than 0.05 comes, we will accept the alternate hypothesis, or If it is greater than 0.05, then what the null hypothesis. So since in our scenario, what happened is the p-value is 0.314, which is obviously greater than 0.05. So it is coming somewhere around here, 0.314. So that's why we are accepting the null hypothesis. Got it? Any question? Okay. So we pass the mean as 150. The number of, so why we are using Z test here? Because the data set which we have is having more than 30 records, right? And also we know the standard deviation, right? The standard deviation is also known to us, which is 2cc. Okay. Anyways, if it is greater than 100, you are using Z test. Okay. Let's look into one sample t-test. One sample t-test. I hope you are able to relate with the theory and the practical, right? One sample t-test. Can someone tell me when to use a one sample t-test?
When sample is less than 30.
When sample is less than 30, right? So let's look into a scenario where we have sample less than 30. So we have imported all this. Let's create a data set, volume pd.series. Okay. I'm not importing anything from a CSV file because I have to again share that CSV file. It will take some time. Let's take some value, for example, 148.5 and then 153 point whatever it is 4 and then 150.9 random samples. You can take whatever you want. 51.2. Okay, so I'm taking 4 data points. Okay, and then let's look into the data. My bad. Right, so you have 4 data points. Mean is 151. Okay, standard deviation is 2.004 and so on. Okay, now you do the same thing, but as I said, we don't have Z test in SciPy, right? We don't have Z test in SciPy, but we obviously have the t test. Okay, so I just want to make sure that you know all of them. So stats. Yeah, so you have t-test one sample. So we'll be using this t-test one sample, right? Because we are doing for one sample t-test. One sample t-test. And in here, let's use volume, which is our data, and then just pass the mean value. Okay. So what we get is the statistic value of 0.9975 and a p value of 0.3920. Now again, 0.3920 is greater than 0.05, right? Greater than 0.05. So null will get accepted. If I go back to my example of t-test, you can see that average was 151. Yeah, the t calculated value is somewhere around 1. And here the null hypothesis was 150 cc. So we can say that the mean of the bottles is 150 cc, which is the null hypothesis. Right? So you don't need to remember everything. You just need to remember that what is the function to calculate the t-test. So we can use the stats library to calculate the t-test, which is t-test underscore one sample. Just pass the data and the mean. Okay, and it will calculate the statistic, which is the z statistic or z calculated value. Here it was 1, right? We calculated 1, but based on this data, it is 0.9975, which is very close to 1. And the p value which is getting generated is 0.392. And this 0.392 is greater than 0.05. That's why if p is high, h0 will fly. So you have to accept the null hypothesis. If p is low, null will go. Okay, so in that case, you any question? So now you understand how to do this both practically, and theoretically. You don't need to remember theoretically. So the question sets which we'll be sharing, in there you will find that what are the conditions of a Z test. So the condition of a Z test is that the population is greater than 30, sample size is greater than 30, greater than equals to 30, and you know the population standard deviation. Okay, or you know the population standard deviation. And for a t-test, the standard deviation of the population is unknown and the sample size is less than 30. So since the standard size sample size was less than 30, which is 4, we used a t-test here. Okay, likewise we'll look for all of them. So Z test and t test is done. In the next class we will look into one proportion test, one variance test. Okay, both theoretically and practically. And then we'll move to two samples. So for example, if you have two machines, how the machines are the results of the machine compared to each other, right? So in that case also we'll use Z test, t test, paired t test. There's a new concept of paired t test in a two sample case. And then we'll look into two proportion test, two variances, and with more than two samples, we'll look into ANOVA, which is very, very, very important for your interview questions. Okay. Any question before I take or before I complete today's session? I wanted to complete the the one proportion test as well, but we'll do that in the next class. Any book suggestions for stat? Okay. I will share a PDF with you. Okay, let me check if it is in my Google Drive. Okay, I will share a statistics book with you, but I am a little worried that it might get a little overwhelming. Okay, it might get a little overwhelming where you see that there are lots and lots of concepts which are more theoretical, and practically it is not possible. But yes, I will share the PDF book with you so that you can go through it. And if you have any question, do let me know. Uh, mm, and ideally, we will be completing the stats portion by next weekend, and followed by uh, assignments of stats, interview questions of stats. We will discuss this in class one-on-one also, if you have any question or doubt. And we'll quickly move on to machine learning. We will go through machine learning and the use cases of machine learning in day-to-day scenarios, and followed by, once the machine learning part is over, we will go through the practical projects of machine learning. I will also go through the entire life cycle of a machine learning model. So you will never get a CSV file, a clean CSV file which you get in a difficult type of JSON file or XML file or a PDF document. Can you quickly repeat Z test in Python missed due to bad connectivity? No problem. I will quickly go through Z test now. So the first thing to understand with Z test is that when we use Z test, when we have more than 30 number of samples and we know the standard deviation of the population, okay, or we know the standard deviation of the population, so either one of them. Now we know that the we have a data set which is machine one in machine 1.csv, and if I look into the data frame, what I can see is the number of count is 100, which is obviously greater than 30. And that instance, we will use Z test to, infer the mean. So I hope you all remember that this, whatever we are doing for Z test and T test is for mean. Okay, so this is for mean, right? This is for mean. So we are actually comparing the mean, okay, the population and the sample. Now what we just wanted to show is through a visualization graph that how the data is spread from 146 to 154, not our problem. And then we also looked into the data. If it is more than 100, it's always good to look into the data through visualization. And we don't have any outliers, and the mean is also very close to 150, probably 150.2. And we just use one line of code, okay, to infer Z test. We use the weight stats.ztest, okay. We pass the data which is present in the data frame, column name machine1, and the mean value of the entire population was 150, so we passed 150. The alternative was two-sided because we were using a two-tailed test. Why we are using a two-tailed test? Because here the question is, has the mean volume changed? Right? The question is, has the mean volume changed? Let me just copy this. Right? So this was the question, has the mean value changed? So in that case, we use the two-sided. We'll also look into how to look into the one-sided graphs as well in the next class. So we just need to change this parameter. And this is how you calculated the Z test. In the Z test, what you get is the Z calculated value, right? The Z calculated value, which we also found using this formula. So in the background, they're using this formula to calculate the Z calculated value. You have the Z calculated value as 1.00603 and the P value or the significance value. The P value is 0.03149. How to decide between one side and two side? Yes. So it is the question, right? The question says that, has the mean volume changed? Okay. So it can either change in the left hand side or the right hand side. Say for example, if your mean value is 150, right? It is 150. So in that case, if this is the mean value 150, if it changes, it can either change in the lower side direction or the higher side direction, right? But if I change the question to has your mean volume increased, right? Has your mean value increased? In that case, what will happen is you will only look into the higher side, right? As I told you that there are three types of tests. One is the lower tail test, right? The lower, if I ask you, has the mean value decreased? So in that case, you'll use a lower tail test. Has the mean value increased? You'll use the upper tail test. Okay. And if it is not mentioned, if it is just mentioned that the mean has changed, okay, you will use a two-tail test. Okay. So for a two-tail test in Python, we will use the two-sided. Okay. The parameter is actually present in the z-test function. So if you want to check, you can use the tab. You can hit the tab just to check what are the parameters it can take. Okay. So this is how we calculate for one sample z-test and one sample t-test.